unit is dedicated to chemical reactions or chemical changes. So the first thing that we need to do is actually identify and explain what a chemical change is, describe evidence of a chemical change, and then have me show you how we actually represent that chemical change in this class. So the first thing, what is a chemical change? A chemical change changes the identity of a substance. So last semester we discussed 5 different evidences of a chemical change, and we're going to be seeing a number of these as we look at different chemical reactions. The first evidence that we talked about is that it can produce an odor, and this is the only one that we really can't represent with a chemical reaction. The next one is that a gas can be produced. And what we would observe if a gas was produced, we would observe bubbles. Okay? The third is that a solid could be produced. And we call that a precipitate. A precipitate forms, and we're going to see a number of precipitates forming in this unit. Okay? The fourth is that the color of the substance could change. And while that would be really hard to show in an actual chemical reaction, we might see a solid forming and know that when that solid forms, that the color of the substance would change. So color and odor are really 2 changes we can't represent in a chemical reaction. The last one is a change in temperature. Okay? And if the temperature of your solution in your reaction increases, that's because you have an exothermic reaction, meaning heat is leaving the reaction. And so what we actually experience as experimenters is an increase in temperature. Okay? If instead the temperature decreases, then it is an endothermic reaction. The reaction itself is taking in heat. And so as a result, it's taking in heat from its surroundings. So if you were to measure the temperature of the solution, the surroundings, would actually decrease. Okay, so those are your 5 evidences of a chemical change. Now let's actually start working with chemical equations. So obviously this is not a chemistry example, but I wanted to show you explain a couple of things in everyday terms. So the first thing that I wanted to talk about was what these are called and what these are called. Okay? These are my reactants. So that is what goes into the reaction to begin with before they are allowed to react. And your products are what are formed, what are produced. Okay? A couple of other things that you will see. So I'm going to represent tires with a T and let's say the body of the bike with a B. Okay? So notice I have 2 separate tires here. So I'm going to represent that with a 2T. And the 2 in front tells me I have 2 individual tires. Now, if those tires were connected to each other, if they are actually attached, the way I would represent those tires would be T with a subscript 2. So that's one thing for you to note. This right here is a subscript. And it is used to show or to imply that the atoms that it's referring to are attached, while this right here is a coefficient. And lets us know that, hey, they are not actually chemically attached to one another. Okay? So 2 tires that are not attached to each other react with, let's say, the body of a bicycle to produce, so that arrow means to produce. Well, what do you have? You now have the body of a bicycle and 2 tires that are now attached to the bicycle. So it's going to be subscript 2. So you could have written, obviously this is a made up example, but B T2 or T2B doesn't matter for this question. Okay? So that is what a chemical reaction looks like. Okay? So what is the difference in this example problem? What is the difference between Cl2 and 2 Cls? Okay, well, in Cl2, you're going to have 2 chlorine atoms that are chemically bound together, just like the tires were in your products. In 2Cl, you'll have 2 individual chlorine atoms. Okay? All right. Some other things that you will see when you're looking at a chemical reaction, you will see different states of matter. So let's talk about them. If you see an L, that means you have a liquid. And the important thing for you to know is that that liquid is going to be a pure substance. So what do I mean by that? It will be, for example, it could be a compound, it could be water. Okay, it could be bromine. Right? Anything that is a pure substance, just either one type of compound or one type of element. To which you say, well, okay, wouldn't it always be that? No. So the other state of matter you could have would be aqueous. Okay? And an aqueous means that you have a solution. Or as we called it last semester, a homogeneous mixture. So for example, if I take salt, NaCl, and I dissolve it in water, that is now an aqueous solution. Even though it looks liquid to you, because it is now a mixture, because I took one compound and dissolved it in another, I have a mixture, it is now an aqueous solution. Okay? The next state of matter, G, stands for gas. I don't think I need to explain that one. And then S stands for solid. So those are the 4 states of matter that you will see in this class. All right, in this section, in these notes, we're going to practice balancing. Now, some of you might have a lot of experience with balancing. Some of you might not have any. That's perfectly fine. I first wanted to explain why we balance chemical reactions before I actually gave you some examples. So we balance chemical reactions in order to follow the law of conservation of matter. So let me write it out and then I'll explain it. And what the law of conservation of matter tells us is that matter cannot be created or destroyed. So what exactly does that mean? Well, let's look at an example. Here I give you, right below, I give you a balanced reaction. Okay? And so what exactly does that balanced reaction tell us? All right. So if you notice for hydrogen here, I've got a 3 coefficient and a 2 subscript. So I have in order to determine the number of atoms that I have of hydrogen, I'm going to take a 3 and I'm going to multiply it by 2. So I know I have 6 hydrogen atoms. I have 2 nitrogen atoms. Okay? And then looking here at NH3, this 3 behind hydrogen only applies to hydrogen. Okay? So what that tells me, the 2 applies to both the nitrogen and the hydrogen. So I have 2 nitrogens, because the nitrogen doesn't have a subscript, and I have 6, because 2 times 3, hydrogens. So what the law of conservation of matter is telling me is that I cannot create or destroy atoms. So if I start with 6 atoms of hydrogen, I have to finish with 6 atoms of hydrogen. If I start with 2 atoms of nitrogen, I have to finish with 2 atoms of nitrogen. Okay? So that's why we balance. Now, the only way to balance, you cannot change your subscripts, right? So this subscript's here, this subscript's here, this subscript here. You cannot change those, because by changing those, you are actually changing the identity of the substance, which you are not allowed to do. So instead, the only way to balance is to use coefficients. So these here are the coefficients that I was able to add in order to make sure that my reaction was balanced. Okay, so let's look at a couple of examples. For example 1, okay, I'm going to go through and explain my thought process. All right, I first look, I've got 1 silver on my reactant side. I've got 2 silver atoms on my product side. So I know I'm going to have 2 silver atoms on my reactant side, so I'm going to put a 2 here. Okay, now what does that mess up? Well, that messes up my iodides, because now I have 2 iodides. Okay, and I have 3 iodides on my product side. Okay, well, how the heck can I make 2 and 3 equal to each other? Well, what I could actually do is make them both equal to 6. So what I'm going to do is I'm going to get rid of the 2. I'm going to make that a 6. I'm going to make this, in order to make iodide 6 iodides, I'm going to make this a 2, because 2 times 3 is 6. Okay? Let's go back and see what I messed up this time. I have 6 iodides, I'm good. Now I have 6 silvers, and on my product side I only have 2 silvers. So what I'm going to have to do is put a 3 in front, and that'll give me 6 silvers. So I'm good there. For iron, I've got 2 irons on my reactant side, and I've got now 2 ions on my product side because I put a 2 coefficient. Okay? The only tricky thing when you have polyatomic ions, I like to, as long as I have my polyatomic ions staying the same on the reactant and the product side, which I do here, then I like to treat my polyatomic ion all together. So I have 3 carbonates on my reactant side, and if you notice now, I have 3 carbonates on my product side. So I am now balanced. Okay? All right. For number 2, I've got C2H4O2, so I'm going to first deal with my carbons. I always like to deal with what's the most obvious first. What looks the most, I would say, scary to me is oxygen, because every single molecule here has an oxygen. So I'm going to deal with that last. Okay? So I've got 2 carbons on my reactant side. I've got 1 carbon on my product side. So what I'm going to need to do is put a 2 in front of carbon dioxide. So now I have 2 carbons on reactant and product side. Then I notice that I have 4 hydrogens on my reactant side and only 2 on my product side. So what I'm going to need to do is put a 2 in front, because then 2 times 2 gives me 4. Okay? Then for oxygen, okay, I've got 2 oxygens on my reactant side and another 2 on my reactant side. So when they're separated, you will then add them. So right now I have 4 oxygens on my reactant side. On my product side, I've got 2 times 2, so that would give me 4 oxygens, and 2 times 1, which would give me 2 oxygens. So I've got a total of 6 right now. Okay, well, I really don't want to mess with this molecule right here, because I used it to balance my carbon dioxides and my waters. So what I can actually do is say, okay, I've got 2 oxygens from here. How many oxygens would this oxygen have to give me in order to get 6 oxygens total? And the answer is I need 4 oxygens, because 2 plus 4 gives me 6. Well, what coefficient would I have to put in front of oxygen in order to get 4 oxygens? 2. And I'm balanced. Okay, let's look at a slightly trickier balancing. I have C8H18 reacts with oxygen to form carbon dioxide and water. So again, I'm going to first balance my carbons, then my hydrogens, and then my oxygens. So carbon, I've got 8 on my reactant side, so I'm going to put an 8 in front of carbon dioxide. Then I've got 18 hydrogens on my reactant side. So what would I have to put in front of water in order to get 18 hydrogens? Well, I would need to put a 9, because 9 times 2 is 18. Let's figure out how many oxygens I now have. Well, on this side here, I've got 16 oxygens, because 8 times 2 is 16. And I've got 9 times 1, which is 9. So I right now have a total of 25 oxygens. Okay, so this is the only thing that contributes oxygen, and I need it to be 25. How in the world can I make that 25? Well, if you think about it, what times 2 gives me 25? Well, 25 over 2. To which you say, oh, that's really easy, and I can be done. Unfortunately, you can't leave a coefficient as a fraction or a decimal. It's got to be a whole number. But here's something really easy you can do. I can multiply my entire balanced reaction, which this is, by one single number, and it will stay balanced. So what could I multiply 25 over 2 by to make it a whole number? Well, I could just multiply it by 2. So this is there's an implied 1 for your C8H18. So now that's going to become a 2. I'm going to multiply 25 over 2 by 2, so that gives me 25. 18 by 2 gives me 16, and 9 by 2 gives me 18. Okay? If you notice there's a lot of crossing out, that is why I ask that you guys write in pencil for this class. You're going to make a lot of errors while balancing. That is perfectly fine, but please make sure that you're writing in pencil. Okay? For the last one, zinc sulfate, okay, reacts with lithium carbonate. Okay, so I've got one zinc on my reactant side, one zinc on my product side. Okay, sulfate remains sulfate. I've got one sulfate on my reactant side, one sulfate on my product side. Lithium, I've got 2 lithiums on my reactant side, 2 lithiums on my product side. Carbonate, I've got 1 carbonate on my reactant side, 1 carbonate on my product side. So I'm actually already balanced. So notice when I have blanks here, I don't put 1s in front because by not having anything, it's implied that it's a 1. So I don't have to write anything. This is already balanced. So now that we've talked about how to balance reactions, we're actually going to work on writing out those reactions. But before we can do that, I need to explain this one concept, which is diatomic elements. Now, these are elements that cannot exist by themselves, okay? And they include nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and then hydrogen. So notice I made a 7. I'll write these out. I made a 7 on the periodic table, okay? There are a total of 7 elements that are diatomic, including hydrogen. And so what that means is if you are writing a reaction and I say, oh, fluorine gas reacts, you wouldn't just put F. You would put F2. And that's because fluorine by itself is not stable. So these 7 elements are not stable by themselves. Okay? So with that in mind, let's actually work on some practice. All right, so we're going to write out our formulas for these reactions and we're going to make sure to balance them. It tells me sodium hydroxide reacts with iron 2 chloride to form sodium chloride and iron 2 hydroxide. So yes, we're going to be working on writing out our formulas again. So sodium hydroxide, to write that formula, I need to cross my charges. So sodium has a +1 charge, hydroxide is -1, okay? And so when I cross my charges, I get NaOH. So I'm going to write this over here. So NaOH is one of my reactants. One of my other reactants is going to be iron 2 chloride. Okay? Chloride is Cl with a -1 charge. So when I cross my charges, I get FeCl2. Okay? That produces sodium chloride. So Na has a +1 charge. Chlorine has a -1 charge. So this is going to be just NaCl when I cross my charges. And iron 2 hydroxide. Fe has a 2+ charge. Hydroxide has a 1- charge. When I cross my charges, remember hydroxide has to be in parentheses, so you have 2 hydroxides. Okay. And I'm good to go. Now, I do need to balance. So I've got 1 sodium on this side, 1 sodium on this side. 1 hydroxide here, 2 hydroxides here. So since I have 2 hydroxides on my product side, I need to put a 2 in front of sodium hydroxide, which is going to mess up my sodiums. Now I have 2 sodiums, so I need to put a 2 in front of NaCl. Okay? I have 1 iron on my reactant side, 1 iron on my product side, 2 chlorines on my reactant side, and now 2 chlorines on my product side. So I am balanced, and that is your first reaction, taking it from words and converting it into chemical formula. All right, let's look at the next example. Sodium chloride reacts with fluorine gas to produce sodium fluoride and chlorine gas. All right, sodium chloride. So sodium has a +1 charge. Remember, I'm crossing charges because these are ionic compounds. Chloride is 1-, so this is going to be NaCl. Reacts with fluorine gas. Remember, I had noted that fluorine is one of your diatomic elements. It cannot exist by itself. So instead of just writing F, you're going to have to write F2. Now notice for NaCl, Cl can exist as just Cl. You don't need to have a subscript 2 here because it's not by itself. It's got sodium with it, okay? That's going to produce sodium fluoride, so Na has a +1 charge, fluorine has a 1- charge, so when I cross charges, that's just going to be NaF, and chlorine gas, which is going to be Cl2 because it is diatomic. It's one of my 7 diatomics. Now I just need to balance. I've got 1 sodium, 1 chlorine, 2 chlorines on my product side. So I need to put a 2 in front of sodium chloride. That now gives me 2 sodiums on my reactant side. So I've got to put a 2 in front of sodium fluoride on my product side. Now I've got 2 fluorines on my reactant side, and now I have 2 on my product side. So I am balanced.